Welcome friends. So today 26th of August, Sunday. So here we go with our set 7. So let's start. So our first question reads, a particle moves in one dimension under a potential V of x equal to alpha mod x with some non-zero total energy. Which one of the following best describes the particle trajectory in the phase space? So you are given 4 figures. So the potential is given as V of x equal to alpha mod x. So if you draw the potential versus distance curve, then we get a curve like this. So if x is greater than 0, when x is greater than 0, it is like this, and when x is less than 0, the curve shows this character. So for x is greater than 0, we have to put b of x equal to alpha x. So total energy E equals to px square by 2m plus alpha x. Therefore px square equal to twice me minus twice m alpha into x. Therefore that is equals to twice m into E minus alpha x. And for x is less than 0, E equals to this. Therefore px square equal to twice m into E plus alpha x. So as you can see from this equation, px square equals to root over this. So this will give you a curve like this. And for this, look, px square equals to minus twice m alpha x. This is equation of parabola. Fine. Now plus 2me term is there. So the origin, instead of being here, the origin is shifting towards positive x-axis. So the resultant curve is like this. And for this, it is this. So for your convenience, I have drawn 2 figures for generalized case. This is for y square equal to 4x. So the curve looks like this, and for y square equal to minus 4x, the curve looks like this. Now if some additive term is added here, then it will shift towards this, and if some positive term is added here, this thing will shift toward this, and as a result of that it will produce a figure like this, and it is matching with option A. Now question number 2. The phase space trajectory of an otherwise free particle bouncing between 2 hard walls elastically in one dimension is. Now for a free particle, potential energy term is 0, so the total energy E equals to p square by px square by 2m. Suppose we are considering only x dimension, means x, y, z 3 coordinates are there, so we are considering x. So px is equal to twice me, so px equal to plus minus root over twice me. So it's basically constant, it doesn't depend upon the distance x. So plus 2me, this is plus 2me, this is minus 2me. So the resultant curve is a phase space curve is a rectangle, which is matching with option C. So the phase space trajectory of an otherwise free particle bouncing between 2 hard walls elastically in one dimension is a rectangle. Now coming to question number 3. Which of the following figures best describes the trajectory of a particle moving in a repulsive central potential V of r equals to A by r? A is greater than 0. So as you can see, this is repulsive force, repulsive potential, A by r. So if you take derivative, then you will get force, and from this you can from the form of potential, as you can see, it has told repulsive. So in case of repulsive potential, the motion will be unbounded, and the resultant trajectory will be of a scattering type. So as you can see, this one is bounded, this one is also bounded, and here here it cannot be an option because it is going towards the center. But for only this case, the particle is scattered, so option 3 is the correct option. Next, question number 4. A particle moves in one dimension in a potential V of x equal to minus k square x to the power 4 plus omega square x to the x square, where k and omega are constant. Which of the following curves best describes the trajectories of this system in phase space? Okay. So first, to solve this problem, we have to find out the form of this potential where its maxima and minima exist. So to do that, we write dv dx equals to 0 to find extrema or maxima or minima. So taking derivative of v with respect to x, we get the positions of extrema at x equal to 0 and x equal to plus minus root over omega square by 2k square. Now if we check further, this will be double derivative, then we can see that x equal to 0 is a minima and x equal to plus minus root over omega square by 2k square, these are maxima. And keeping in mind these things or data, we can draw the potential energy curve. So the potential energy curves looks like this. Look, if you know the form of potential, you can draw it on your mobile using some curve, some software. I am telling you the name of the software. The software name is Desmos, DESMOS. So you can get it on Play Store. So you can download it and you can visualize the form of any kind of graph using that software. That software is really good. Okay. Now to draw the phase space, we have to draw a curve between its momentum and position. So as you can see, if we take this energy, suppose this is energy level 1. So for energy 1, the motion is bounded. Okay, so we get an ellipse-like structure. Now how far it is bounded? Up to this point. So it is reaching its maximum limit, and after that beyond this, if you take a more higher energy, then the motion is unbounded and get the curves like this. So it is matching with option 2. So second option is the correct option. Next, coming to question number 5, the Hamiltonian of a particle of mass m is given by h equal to p square by 2m minus alpha q square by 2. Which one of the following figures describes the motion of the particle in phase space? Okay, so as you can see, this is the Hamiltonian, and from here we can write this is the potential. So we know the potential for plus half kx square, that is that is a parabola, but a minus sign is there, so it is inverted parabola. Okay, so we got the form of the potential. Now we have to draw the phase space trajectories. So as you can see, if you write it p square by twice m minus q square by twice c by alpha equal to 1, so it's basically the equation of hyperbola. So the phase space trajectories will be hyperbola. So all the given options are of hyperbola, but to find out the correct option, we have to remember the properties of phase space trajectory. One of the properties of phase space trajectories is that the direction of phase curves is in the same direction in each coordinate. And in a particular coordinate, the direction of phase curves is in the same direction. So as you can see, for option yes, in every option this point is not usable here, because in all the options it is maintained. So we have to find out some another condition. So p square minus alpha m q square by twice m. So if e equals to 0, then we can see that p equals to plus minus root over alpha m into q. So this is basically the equations of straight lines. Fine. So these are the straight line. They are not intersecting each other. So as you can see, the dot sign is here. This point is called saddle point. They are not cutting each other. intersecting each other. That's a basic property of phase space trajectory. Now from the sign convention we can say that when particle is coming from negative x to positive x, the momentum has positive sign, and vice versa, means when we are coming from positive x to negative x, the momentum has negative sign. So we will apply this logic to choose the correct option. Now as you can see here, for this option it is going from positive x to negative x, so it should be negative but it is positive, so this option is discarded. For this also, this is also discarded because we are going from positive to negative, but the momentum is here positive, which is violating that principle, so this cannot be a possible option. And for this, what's wrong with it? Okay, so this, but here you can see the direction is here in this direction and the direction is here in this direction, so it is also not possible. So the possible answer is this. So as you can see, it is going from negative to positive, so it should have positive momentum, and here it has positive momentum. So option D is the correct option. So you have to apply all the properties of phase space trajectory to find out the best option. Now question number 6. The Lagrangian of a free particle, relativistic particle in one dimension of mass m, is given by L equal to minus m into root over 1 minus x dot square, where x dot equal to dx dt. If such a particle is acted upon by a constant force in the direction of its motion, the phase space trajectory is obtained from the corresponding Hamiltonian is R. So Lagrangian is given. So from Lagrangian we can find out P equals to dl L dl x dot equal to mx dot. Therefore Hamiltonian is given by H, function of position and momentum, px dot minus L. So if you put the values or replace the values of x dot, because Hamiltonian is not function of x dot, so we have to replace x dot. So you can replace x dot from this expression. So upon replacing that, we get H equals to this expression. So that is equals to root over p square plus m square. Hamiltonian in the presence of constant force in the direction of motion is, so Hamiltonian equals to this, and in presence of constant force, which is given in the question by a constant force, an additive term is added here, v of x. Now constant force, for f equal to minus dv dx, therefore v equals to minus f into x. Fine. So we are considering only the magnitude, so plus fx. Therefore E minus fx, or if you can take a plus value here, minus value, then also you will get the same equation. So E plus fx square by m square minus p square by m square equal to 1. So this is basically the equation of hyperbolas. So some calculation mistake is there, I think. So but the answer, main answer will be same. This is an equation of hyperbola, so the phase space trajectories are hyperbola. Next, question number 7. The dynamics of a particle governed by the Lagrangian L equals to this describes. So what we are doing, we are taking derivative with respect to x dot, del L del x dot equals to mx dot minus kxt, and del L del x equal to this. So from Euler-Lagrange equation, ddt of del L del x dot minus del L del x equal to 0. Therefore we get mx dot equal to 0, which is the equation of a free particle. So the correct option is a free particle. Now question number 8. Which of the following figures is a schematic representation of the phase space trajectories, that is contours of constant energy of a particle moving in a one-dimensional potential, v of x equal to minus x square by 2 plus x to the power 4 by 4. Okay, so first we will try to draw the potential energy curve. So minus x square by 2 plus x to the 4 by 4. So the potential energy curve looks like this. If you know the form of the potential, then it's very easy to draw, and you can check it using the software Desmos, as I told you. So the potential energy curve will look like this. Otherwise you can find it out manually by finding its maxima and minima. So as you can see, it has 3 extremas. Now to find out the maxima and minima, we take double derivative of this potential. So d square v by dx square at x equal to 0 gives minus 1, which is less than 0, so it's basically maximum. So x equal to 0 is a maxima, and x equal to plus minus 1, it gives d square v by dx square equals to 2, which is greater than 0, so x equal to plus minus 1 are minima. So as you can see, 3 minus 1 plus 1, these are all minima, and this is maxima. So we are considering several cases. So first case, minus 1 by 4 less than e less than 0. So the energy level is here. So as you can see, it is cutting at this point, this point, this point, and this point. And the particle has motion about this stable equilibrium point, and the motion is bounded. So this gives ellipse. Now when the energy E equals to 0, the particle can be landed exactly at unstable equilibrium. So it gives phase space trajectory like this. Next, case 3, if 0 less than E less than 0 infinity, the particle has motion about unstable equilibrium point x equal to 0. So the motion is also bounded here. So the resultant phase space trajectory is this, and it is matching with option A. So option is the correct option. Now coming to question number 9. The Hamiltonian of a classical particle moving in one dimension is h equal to p square by 2m plus alpha q to the power 4, where alpha is a positive constant and p and q are its momentum and position respectively. Given that its total energy E is less equals to E naught, the available volume of phase space depends on E naught as. So to solve this problem, we have to find out this integration. So as you can see, the form of the potential is this alpha q to the power 4, and it gives a curve like this. So this is the potential energy curve. Now we have to find out the phase space, volume of phase space. So the phase space curve is like this. So basically an ellipse. So what we are doing, we are calculating the volume of this part and multiplying it with 4. So 4 into, so we have to find out the phase space corresponding the energy E naught. So it is corresponding to Q naught. So this integration we have to find out. So we are replacing P from this expression, and dq remains the same. So we have to find out this integration. Now to evaluate this integration, we are assuming that q equals to E naught by alpha to the 1 by 4 sine to the 1 by half theta. So dq equals to this. So if you don't need to evaluate this integration completely, but you just need to know about the involvement of this E naught. So E naught to the power 1 by 4 here, and E naught to the power half here. So phase volume is E naught to the power 3 by 4, which is matching with option E. Now finally question number 10. Which of the following set of phase space trajectory is not possible for a particle obeying Hamilton's equation of motion? So as I told, to solve this problem we have to look at the properties of phase curve. So the first property is for given values of energy, phase curve will be unique, and the second property is the phase curve will never intersect, and third, the phase curve can be bounded as well as unbounded. So to solve this problem, you have to utilize this property, second property. The phase space curve will never intersect. As you can see, it is not intersecting here, but it is intersecting here at this point and this point. So this cannot be the possible phase space trajectories. So option B is the correct option. So this is all for today, guys. If you like the video, please like it and share and subscribe my channel, and don't forget to press the bell icon. And if you want to get the lectures on phase space trajectory, you can find it on the description. And if you have any question, you can comment down below. And finally, thanks for watching.